Let's start 5.3. So in this chapter is mainly about internal resistance and EMF. Okay, this is the main course basically. So right now I want you to read the textbook on page 227 and 228. Pause the video now and come back to me, and I want you to tell me what kind of keywords there are. Okay, so let's go through it together. So on the first page here, and it actually doesn't have much new idea, which most of the idea here has already been covered in 5.2 already, and so I'm not going to repeat them. The basic idea of this is saying you can consider the circuit as like a water pump system where it can pump up the water and store gravitational potential energy. And pump is the battery, and the wheel is simply the resistor. And yeah, something about the energy. So I think you basically learn all these things in year 10 already, so not something that is very new to you. The new thing, however, is you now have to distinguish the idea of EMF to voltage. Alright, and in the past when we talk about EMF, the full name is actually called the electromotive force. Okay, if you want to write down electromotive force, so that's why you have E, M, and F, and that is not really a force. We call it a force because simply in the history people thought it is a force in the circuit pushing the electron or pushing whatever in the circuit to power up the engine or the motor, etc. But later on people find out it is not, right? As you may have learned in year 10, we learned that it's actually something called current. It's not actually a force to push the electron to move. And the voltage is there to provide you energy, more likely. So this is just a name, right? We'll still keep the name as we had in the past to kind of respect the history, but then please understand that this is not actually a force. All right, they are not equivalent, and also the unit, of course, is not Newton. All right, it's volt V. So the difference between EMF and voltage is that voltage is a more general name to refer to potential difference. So how much voltage drop, basically, potential difference. While for EMF is only referring to the potential difference on the battery. Okay, so that's why you see here when we say in reality there is internal resistance, all right, which is simply the resistance within the battery, because think about how people make a battery. Inside there must be some connection with some metal or some other things, and that will surely take up some energy, and therefore there must be some internal resistance in it. And so here you can see that in the graph, in the picture, we draw a small resistor here using the small r, lowercase r, to represent its resistance, and you can see it's embedded into the battery also. Okay, and so if you try to measure the voltage outside of the battery, then it will not be exactly equal to EMF. By the way, EMF symbol is this one. All right, I can draw it here. This is called epsilon. So when there's no internal resistance, this is a picture of the battery when there's no internal resistance. This is how you treated the circuit before this chapter, or in year 10 also. That is voltage equal to EMF simply. So the world is much simpler, but now your world is getting more complex. So what happened is we now acknowledge there is internal resistance, and so this internal resistance would surely take up some voltage, right? Let's say it is a VR, or V small r, and so if the real battery, I mean if the whole battery in itself provide you a certain amount, so epsilon, let's say 10V. All right, ideally it provides you 10V. However, this internal resistor will take up, let's say, 2V of the voltage. And so what you could have outside is, you can imagine that the whole battery in itself could provide you 10 in theory, but then now it's taken by this little EVO, which take up 2 volts. And so when you try to measure outside, you only get how much? You only get 8V in that case. All right, and the idea is simply you have using this equation, which is, or you can see here, which is bigger, then you can imagine it's a bit like x equals to 10. 10 is the original one, minus the 2. All right, 2 is taken from the the internal resistance here. And so the way to evaluate the internal resistance is, of course, if we have an ammeter, then we would know the I, which is the current, and so we can represent this 2 is the voltage, by using V equals IR. And that's why we use IR here. Because normally we cannot know how much voltage drop on the small resistor, because you cannot have, if you think about it, like you cannot have let me change the color. You cannot put the voltmeter like this to measure the small internal resistance, how much. It's impossible because it's inside the battery. And in fact, it is not really one piece of resistor put inside. No one actually wanted to put one piece of resistor. It's simply because of the design, structure of the battery, and therefore you had some, like a small amount of resistance inside the battery. A bit like the connection wire. In reality, all the connection wire also carry a very small amount of resistance also, no matter how good or how expensive the wires are. Okay, so that's why the equation would be this one, V equals to epsilon naught minus IR. You may see some textbooks or some website, they will write more like this, epsilon naught equals to V plus IR. So this V is, you may want to refer that this is more like external one, like the voltage actually got used by the external component, while this one is the voltage taken by the internal resistor. Okay, and this is the actual EMF. That means the ideally maximum voltage output by the by the battery. Okay, so right now what I will want you to do is, there are 2 questions, which is an example actually. I want you to try it out, pause the video, and we will talk about it. Okay, so let's take a look at this question. So the question said the potential difference across the terminal is 4.8. So let's identify what it is first. Okay, so if you recall what we talked about, then this across the terminal, let's read the whole question. When the current is this, and 4.4 when the current is that. So that should be both V, I think. Yeah, both of them are V, like the external voltage. And they want you to find the EMF. Oh yeah, so I'm right. EMF of the batteries, this is the unknown, and also the internal resistance, small r. Okay, apparently these are 2I. So maybe I call it V1, I1, V2, I2 in that case. Okay, so this is what you should do when you read a question like this. So what you do afterwards is, apparently you have to use the equation V equals to epsilon naught minus IR, and you substitute the 2 conditions, V1 I1 into 1 and V2 I2 into the second equation. So what I will have is, I will just write directly 4.8 equals to epsilon naught minus 1.2 small r. That's equation 1. And for equation 2, then that will be 4.4 equals to epsilon naught minus 1.4 small r. Okay, so if you call this equation 1, equation 2, then you just have to solve it. Okay, so I think the easiest way to solve it is minus them, right? So that you can get rid of the EMF. So let me try to do it. Sorry, I didn't give you enough space, but then I think I'll just ran over to the run over to the next space. So let's say 1 minus 2. How about that? Okay, so left hand side you only have 0.4, or I'll do a bit faster because I'm running out of space. Epsilon will be cancelled out, so you have maybe I'll still write it out, okay, just to be more careful. Minus the epsilon minus 1.4 out, and so 0.4 equals to epsilon is gone, and you had 0.2 because minus and minus give you plus, right? So it's 1.4 minus 1.2, which is 0.2 out, and so out is actually 2 ohm in that case. Okay, and so that will be the answer. And for EMF, you can simply substitute it back, which let's just do equation 1. Okay, sub it back into 1, and so you get 4.8 equals to epsilon minus 1.2 times 2. Okay, and so epsilon is actually 4.8 plus 2.4, 4.8 2.4, which gives you 67.2 V, and that's how you could find it. Okay, and so this is actually a very good question, where in the next video I'll teach you how to do an experiment, of course using a simulation, because you don't have access to lab right now, and this is an idea of doing multiple trial can help you to find the EMF and also the internal resistance. Okay, so if you haven't tried the next question 5.20, try it now and pause the video. Okay, so let's try it out. For this question, this is also a very typical question that you find in chapter 5 about internal resistance. Even sometimes you find on paper 3. In case you don't know, paper 3 is sometimes asking you about some practical skills, something about data analysis, similar to the things that you learn in chapter 1, asking you about the error uncertainties, error propagation, those things, right? They kind of mix this into those paper 3 questions. Alright, so quite popular in the past. Anyway, so what you find here is you have a graph, which again is something that in the next video I will teach you how to build a circuit, and you will need to use your Excel or Google spreadsheet if you don't have that to construct this kind of graph. But for now, let's try to interpret it first, assuming that you have already got this graph. So if you understand what happened here is you can imagine is simply the circuit that we have, like this, simply a battery. If you don't know what's going on, then you can imagine this is a small R, and this is a battery itself, and then there is simply a I think a resistor outside, and you measure the V, and then you could also measure the current also. Yeah, and then this is how you set up the circuit right here. And so what you have is a graph of these, and it may look quite strange because normally you find the graph looks more like this for V and I, so that you get a positive line. But then how to interpret this is, if you try to understand from the equation, which is V equals to epsilon minus IR, take a look of this equation, and the axis or XY axis of this graph. Try to interpret what it means by epsilon and small r. I'll give you a few seconds. Try to maybe you can try to pause the video, think about it first, and get back to us. Okay, so what you should find out is that apparently V is Y. So what you can do is you can transform the equation as Y first, alright, and I is X, is on X axis, so I itself is X, and so you can put epsilon and R here. So if you try to compare this equation with the usual standard linear equation that you learn in maths. This is still a linear line, right? It's not a proportional line. Proportional means it passes through origin, but it's still linear, right? So you can still use the idea of y equals to mx plus c to model it. That actually means if you try to compare these two, what do you find? You will find that r is m. Not really. Actually, not r. It's not r equal to m. It's negative r equal to m. M is what? M is slope, right? So that means whenever you learn about this, the slope is always the negative r. That means negative of internal resistance. Okay, and actually that makes sense because resistance cannot be negative, right? And if you look at the slope here, the slope here is of course negative. So negative of a negative thing become positive. So the resistance will actually be positive in when you try to calculate it. And if you try to look at the other one, which is epsilon here, and you can find epsilon is simply the constant, which is the y-intercept. Okay, so this is another important idea that you have to remember that. Alright, really, I mean, this is something that you have to remember for physics. Slope is negative r in a small internal resistor, and the y-intercept is the EMF in that case. So what you could do once you understand the idea of these two, then simply obtain it from the graph. And that means what you could do is extend the line. Sorry, I don't have a ruler here, and I don't bother to do that. And so I will try. If you had your textbook, then you can refer to that, but I'll try to do it. Okay, I think this is pretty good already. Don't you think so? So I think about 11. So I think this is y-intercept 11, and that means for this question, EMF is 11 volts simply. And so for the slope, I think we could find a certain point, which is, I think this point is pretty good. Or actually I should use a longer part. So how about this point, and also maybe this point? Okay, and so the slope would then be simply delta y over delta x, and y for this is, I think, 10. Let's write a coordinate. This is 10. How much? This is 5. Wait, 4. 1, 1, 2, 3, 4. 4 grid. So, oh, this is 9. Okay, so this is 8.5. Yeah, 8.5. And so these coordinate is 30 and 3.5. So what you could get is, yeah, I'm right. So 8.5 minus 3.5 divide 10 minus 30, and yes, you of course you get a negative result. And let me get my calculator. You would get negative 0.25, and that will be the slope. And in that case, if you know that the slope is negative r, then you can imagine that actually means negative 0.25, which is the slope, equal to negative r. And so r would equal to 0.25 in the unit of ohm in that case. Oh, I make a mistake. Do you know what that is? My mistake, do I? Actually, I think, oh yes, I still make a mistake. What I'm saying is I'm just trying to check. I mean, this is the habit you should have. Check the unit. This is millivolt, and this is milliamp. So what I did just now, I thought they are just simply V and A. And so if that's the case, then my answers will be correct. But now I think it's not completely correct. Can you point out what that is? Like which part is wrong? So what I think is my resistance calculated is still fine because these two milli, like 10 to the power of -3 will get cancelled out when I try to calculate the slope, because y is simply delta v and x is simply delta I, so they would just got cancelled by when they divide each other. So this is still fine, but for EMF certainly is wrong. Right, this is 11 millivolts instead. Okay, sorry about that, but I think that's the whole idea. Okay, so this is again a very important and useful concept when you try to deal with internal resistor and also EMF.